I am certainly happy to be able to have this opportunity today with my colleagues at NASA Langley to describe this work to you, this work out of the Crew Systems and Aviation Operations Branch at NASA Langley. So I'd like to begin by describing a little bit about the context of the challenge that we're trying to meet with this work. And then I'll move on to describe a little bit of the prior work that's fed into the current technology. Then describe the technology itself, some applicable scenarios, and what investigations are enabled by this technology. And then we'll show you and describe some recent demonstrations that we've achieved for this work. So let me start with the challenge, and that is around human autonomy teaming. We don't currently have a good way of approaching this, a rigorous systematic method for, as it's described here, a systematic method for defining and analyzing the architecture of human autonomy teams. And we think that identifying and detecting and knowing the workload experienced by human operators would be valuable to allocate functions between humans and autonomy. So, and we also see that this teaming is key to achieving urban air mobility or advanced air mobility, where we want to fly on demand from certain very close locations and perhaps someday without even a pilot on board. And so on that note, there are like two camps, so to speak, around that. You know, one camp thinks, well, let's just jump ahead, remove the pilot, you know, that it certainly helps the business case and maybe even enables it to close, and remove that operator completely. It seems like it might be the easier way to go. I count myself in the camp that, you know, thinks that teaming is actually a key to achieving everything we need here. Some advantages to having the pilot on board include getting operations up and running sooner, having more time to learn what the pilot brings to safety in these contexts, in this new mixed national airspace, and also enables folks to take advantage of minimally trained or licensed passenger or minimally licensed passengers. So this is going to be a new regime, and having a pilot on board, at least in the beginning, enables us to learn some of these lessons. Also, humans are still the best at mastering uncertainty in situations that require the application of knowledge, not just running a rules-based algorithm. So, and also costs, you know, it's advantageous to remove, from a cost point of view, to remove the operator, because that's a seat you can put on an urban air mobility vehicle for a passenger. But also the validation and certification methods and accidents are also all very costly. So those have to be considered as well. Okay. So I'm going to move ahead, having motivated that, the study of humans, and describe a little bit about some prior work that's been completed in our branch for monitoring humans and monitoring their physiological signals and using that to predict what state the operator is in. And so you see described here a picture of an architecture that we used. You'll see in the middle various psychophysiological sensors and their signals represented. And you'll see the way that we fuse those signals after their own individual signal processing, extract features from them, and synchronize those data before they're fed to machine learning classification algorithms. And we used that design to output in real time display of state prediction. So this is a separate patent. This is prior work. And you'll see on the left that we employed the same system during benchmark task performance in order to generate training data. And we deployed it during a simulated flight during simulated flight performance with commercial aviation pilots in order to create test data. And the most I've got highlighted here in the upper right for you, the most recent paper that we have on that, which is our best results to date in terms of predicting state. The autoencoding was employed to deal with a lot of biological noise in these signals, which is a challenge. And so we were able to achieve the detection of non-nominal states with accuracy over 80%. And so in this work in particular, we were looking at channelized attention, diverted attention, and startled surprise grouped together versus no event. And so we're able to see when we might need to take a better look at what's going on in the cockpit because something off nominal has occurred, and we're detecting that. I'd also like to note that we're not clinicians, we're not medical doctors, so this was focused on cognitive state. However, we did see that it enables something we call trust in the human operator. And so this gets at what we're used to thinking. We're used to thinking of, does a human trust an autonomous system? But this flips it around and gives the system some information about the state of the human so that it can develop trust in the human operator. Is that operator reliable in this moment? Are they ready to take control? Or should the system perform that function in the moment? So these are the kind of questions we're looking at. And so, we think that this monitoring allows the system to support the operator at the right time in order to avoid the pitfalls of the operator's suboptimal states. And then also the system is going to have its own status, its own state. We'll get to that in a couple slides. Okay, I already described a little bit earlier the way we've developed real-time tools to identify some of these states, and we've gotten into simulating the detection of incapacitation as well, and we'll get into that. And I want to make sure that I note that we're not, with this technology, we're not aiming to solve everything that has to do with human autonomy teaming, but we want to point out what the monitoring of the human can bring to improve that situation and improve the way that the system is built and the way the functions are assigned between the system and the human. So as you see in the middle picture, we have this architecture described where we have the system on the same level as the human. They're truly teaming together. It's not just a human monitoring an automated set of rules that are being executed. Truly, we have to think about this differently when we think about true autonomy and that system making its own decisions, the same way a human would make decisions, and then these two are teaming together. And so we have the output toward the bottom of how that teaming metric is progressing, whatever that's based on. How is that team performance? What does that team performance look like? Are they achieving their goal? Are they getting to their target destination safely and efficiently? And if you feed that information back, you were able to then create an adaptive autonomous system that through dynamic function allocation would decide, because it has knowledge of the state of both the system and the human, it can decide which is best to be performing that function in that moment. And so I'll just note also before moving on is that we've begun to simulate, begun to implement this technology in simulation platforms. And so we aim to do some sim development, but this could also apply to operations, of course, getting that simulation step first. Okay, so let me describe some of the scenarios where and how this might play out and the way we've looked at it. So if you look at the first row, we have the human state being that the human is incapacitated. They're passed out. They don't have there's no control input coming from them, no communication. Maybe the vehicle is moving outside of its intended envelope or flight path. And in this case, it's easy in the sense that it doesn't matter what state the system is in. There is no human input. It has to take over. And so the adaptable autonomous system is, in this case, assigned full control. And you'll see that we've demonstrated the contingency where the system would head toward the nearest medical facility. In the second row, we can think of the situation where the human is attentive and situationally aware. The system is working nominally. However, there's some divergence, there's some incongruence between what the human actions are and their control inputs. And there's a lack of shared situational awareness between the two because the human may be detecting a hazard that the system is not. So one could argue that the system should be designed so that it can detect those hazards, but not if we're not there yet with our systems and we rely on that human's input, the human takes or is assigned full control in this situation and remains engaged and avoids over-reliance on the system. When we look at the next situation, which we've also demonstrated in our labs, the next situation is an overloaded or a distracted operator. And so similar system is not working nominally, but maybe there's a lack of control input from the human, lack of communication from the human. And so these would feed into that teaming metric and feedback that the adaptable autonomous system it would be best if it shared the burden at that point where it can, and to allow the human to avoid and allow the team to avoid under-reliance on the system. And then finally, we can consider the situation where there's a bad actor. Maybe the system is adapting. It's trying to accommodate flight parameter exceedances or unexpected control inputs. Lack of shared intent may be detected, lack of communication, incongruent actions. And so in this situation, if we've identified that there's a bad actor in that human state, then the adaptable autonomous system could be assigned full control, and maybe the controls are restricted from the humans' operations. And so I want to note also that we're not trying to decide how these should go. These are just use cases that we've come up with, and one of the things that's good about building this kind of technology and working with is that it enables some studies. It enables human-in-the-loop simulation studies that will allow researchers to investigate these questions and decide, how do we detect a bad actor? And what do we do? What's the best thing to do about that? So we're really just looking at building the tools to enable that. And so I've kind of already gotten into this slide, talking a little bit about what's enabled. So there are many investigations that are enabled by technologies such as this, so that we can realize a safe and efficient urban air mobility market. How are these systems best designed? How is the teaming best optimized? How can we avoid performance decrement in these new contexts that we're not used to seeing out there in the national airspace? We think about ground control and remote operations. How many vehicles are optimal in those situations? And so, as I mentioned earlier, we're going to have a mixed airspace. And so even if you're in the camp of folks just not having an operator on board, we still are going to need to know something about those vehicles that do have that operator still on board, because the airspace is going to be mixed, and we're going to want to simulate that and do research on it and know about it. Okay, and so here I'm going to move and describe some demonstrations that we were able to achieve. So in order to begin to reduce the concepts to practice, first in our simulation context, we've completed 2 demonstrations. I'm going to show a video of the system for one, which is the incapacitation case, which is the first one. And it took place in the part task simulator that you're seeing pictured here on the left that is modeled after an emerging urban air mobility vehicle design. And you'll see in the video, you'll see that it shows a display, a moving map, and a ground-facing camera. And taking advantage of some of the other technology that's being worked on within our branch. And so you'll see also here on this slide a figure from an IEEE ICAS paper that we can share. And it just gives you the overview of the connections to our simulator. And you'll see pictured an eye tracker. That's a Tobii Pro eye tracker. The participant is also wearing a Muse headband. You can see right above the eye tracker on the forehead. And also you can barely see there's an Empatico watch. So these are the sensors that we've employed in order to achieve these demonstrations to detect the physiological signals and to build an end-to-end system and demonstrate how it might work. So the systems and the signals are real and they're sent in real time during these demonstrations, but the flight aspects are simulated. Okay, so at this point, I want to begin describing the video, and I think I'm going to pass this back to one of our hosts. So let me set the scene while it's coming up. So the demonstration scenario will begin with nominal operations. We begin in flight, on a trajectory, and in manual mode. So we can start. Okay. So operator incapacitation is simulated by sending non-normal signals via the eye tracker worn by the operator. So this simulates incapacitation. The CSM, the crew state monitoring system, detected this and output an indication of an incapacitated state. So upon receiving that signal, the autonomous system enacted contingency operations, which included changing the mode from manual to semi-automatic, as you see displayed there. And that was via our dynamic function allocation control collaboration protocol, which we shortened to de facto. Also, part of that contingency is that an emergency is declared and communicated as needed. And then flight path changes were made. You see the turn being enacted, and now we see the ground-facing camera as well. And so the changes to the flight path were made to change the destination to the vertiport with the closest medical facility. And eventually the system lands without input from the operator. And so the system also receives back an acknowledgement or rejection depending on the current flight simulation mode and potentially upon the operator dismissal of the takeover. So these are some of the things that we've built in just to try to simulate this system and demonstrate it, to demonstrate the system in a flight simulation. Okay, and so the other demonstration, which I don't have a video for you, of the mitigation process in the case of distraction, invokes that de facto protocol to simulate autonomous control of the aircraft. In the case of pilot distraction, the vehicle mode changes to automatic mode and the automation executes the existing operation plan. And so the system will perform the mode change command and, if appropriate, will hold those commands until they're superseded by the operator. So this is some of the cases that we've been able to demonstrate with the system. And so this concludes the technical portion of the presentation.